All right, hello everyone. My name is James Anthony. My last name is unpronounceable by humans, so just please call me Jamie. My presentation is on simulating and testing speculative propulsion devices on a low-thrust torsional pendulum. I am an independent researcher, a hobbyist in this field, probably one of the most devoted DIYers. This is my lab space in my basement. I do all of my simulations in my office upstairs, and I have my 3D printer up in my office as well. I started out in this about 4 years ago when the M drive became, you hit the news real big. I came up with the idea of an optical M drive that used lasers rather than microwaves, and I wanted to test that. Jose convinced me to actually go with a traditional microwave M drive, and I had originally intended on using an air track, which would have worked had the millinewtons of thrust actually worked out, but when you're doing micronewtons, an air track is just not going to work. So I started, this is a very, very early picture. I started a Cavendish type balance. It's all aluminum. I actually incorporated the air tracks down here at the bottom, the idea being that you test it on the torsional pendulum, graduate it down to the air tracks for more thrust. How this worked originally, and I think, Jim, you did this in the past, was I had a laser beam attached to it, and I shined it 30 feet across the room, and I generated this, right, which you have to watch. The power on here, power off here. This is a real pain in the butt doing this, by the way. So you have to come up, you have to process the data, take it into another program, have this exported out, then take this into Excel. I mean, it's just a real, real big pain. So of course, what you need is a laser displacement sensor, which I think Jim uses a Filetech laser displacement sensor. This is mounted at the very end. It shines onto the torsional pendulum arm, and it gives you data. Now the way that this is all, someone actually did this spreadsheet for me, I didn't do it. And so you input, the radius, the mounted radius of your laser displacement sensor, your LDS displacement constant, and your torsion rod length and diameter right there, and it spits out the K factor for you. The important one here being the 0.00326 pound-inch per degree. Now the Fullerton uses the 2 C-Flex E10s. Those are 0.0037 each. Times 2, you get 0.0073. So my torsional spring rate is half of the Fullerton torsional pendulum, and my mounted radius of my laser displacement sensor is a lot more. It's a half a meter.
What's the frequency response of the Filetech device?
The Filetech device has, at the lowest frequency there, I don't remember, I think it has like 200 hertz.
Okay.
But it goes, at the lowest resolution, it goes all the way up to 220,000 hertz, and that's samples per second.
Sure.
Weight limit on my torsional pendulum before the torsional rod becomes elastic, and thank you, Dr. Rodal, he's actually the one who pointed this out for me, is 50 pounds. Having the laser displacement sensor then meant that I could start putting hard numbers to deflections of the beam. Sometime during this, I got a tour of NASA EagleWorks lab. Paul March was very nice to show me everything. I got to see every single experiment and every detail, from their interferometer, the white Jude interferometer, to the M drive, their chamber, and their rotary system that they've been using lately. Armed with that information, I was able to come back to my system. I needed a draft enclosure. You got to have a draft enclosure. Cavendish had a draft enclosure. That's to eliminate, so you can walk around in the room and not disturb the torsional pendulum. So I had, at this particular time, I put everything was on the torsional pendulum. Everything was battery operated. You can see it here. There's the M drive, there's the torsional pendulum, and then that is a reservoir for the viscous dampening fluid that I use. So this was some of the very first data that I was able to produce that was of quality. And this was a powered test at 2 watts that I was conducted sometime in 2017. And you'll notice that I have this really bad noise level here. It's about 5 micronewtons of noise. And that was a problem that I had to work on. Now we go back to simulations. Part of my presentation is about simulating and testing devices. We simulated using FECO, which is an electromagnetic simulation program, a number of different geometries, from hyperbolic to square. We tried, what kind of distortion can we do on the cavity before we lose the mode shapes? Even a helical M drive of some sort. So, we did a whole bunch of that. And then another big part of the simulation is that to be safe, it's always best to test within the ISM band. ISM stands for Industrial Science and Medical Band. That's the only band, radio band, that you can leak onto safely without causing a bunch of troubles. That's also what your microwave at home works on.
And you got excellent correlation between the simulations and your...
Yes,
right.
yes.
And also enable you to actually design even the antennas and so on.
Yes, and I can design the antennas. All the antennas were designed in FECO. Their placement, everything was designed in FECO. So I was able, I also did the convex, concave end caps, all of this going together to create a 3D printed M drive, believe it or not. So I had to print it in several parts because most 3D printers can't print large enough parts. Another thing that I was able to do is design a way to tune the antenna without needing a 3-stub tuner. So I actually tune the antenna inside the cavity by moving the antenna up and down inside the cavity. And you can see I also am able to tune make sure that the 2 ends are parallel by tuning. There's a little copper gasket in here, and tuning these right here allowed me to adjust the parallelism between the 2 end plates. It worked. Now I covered the inside with foil. Basically, it's EMI shielding foil. It works best, believe it or not, at the ISM frequency because it's designed to shield from microwave interference from your microwave at home. It had a fairly low Q. The Q unloaded was 8,000, the Q loaded was 6,000, so I just call it 6,000. It's mode TE013. The big problem with that is since the outside is plastic, it's not thermally conductive, so it's impossible to confirm mode shape with an infrared camera. Another thing that I used the 3D printer for and designed was a liquid metal contact system. This will allow me to get rid of the battery because charging the battery every time. It also allowed me to not touch the pendulum. It's very important to just let the pendulum be alone. To have everything on the pendulum, I can close it up and I don't have to charge the battery. I don't have to make any adjustments to it. Everything, it's actually 4 of these are dedicated to USB, so I have a dedicated USB connection to the torsional pendulum. And the torsional rod actually is right in the middle. So that's why it's shaped like this.
What liquid are you using for conductive?
I use elemental mercury. Now I know that it's toxic, but it's cheap, and there are ways that you can prevent it from. Now this is sealed. This is where the mercury. This is a much higher quality print. It's sealed with chemical sealants, and then once you put the mercury in, you put a couple of drops of oil on top, and that prevents it from evaporating. Right. And Paul March was the one who told me that. And this is what it all looks like put together. Don't laugh. I know it looks rough, but it works like a charm. And it works great. And I've not looked back to going batteries or anything. Now last year when I was invited to the aerospace workshop, I had reserved a couple of weeks before to do tests. And this was the problem that I was having, that same 5 micronewton noise problem. And you're not going to be able to detect 3 micronewton signals if that's a problem. So I started the process of trying to eliminate the noise. All of these bricks, rice to help maybe stabilize the viscous damp. I'm still eating this rice. To help stabilize the viscous damping. Didn't work. All right, so let's try insulating the entire outside of the draft enclosure, see if that worked. Didn't work. Noise problem still persisted. The key was to actually cover the torsional pendulum itself with insulation. Now why that is because it's constructed of aluminum, and aluminum is highly thermally conductive. And when it interacts with the air, it transfers heat and starts to shed vortices. And if there is a change of temperature in the room, say with your body being in it, then you're going to start shedding vortices near your aluminum, believe it or not. And then it opened up the world of sub-micronewton testing for me, and it worked great. So here we have a dual calibration coil test. I couldn't find the original calibration coil test where I confirmed the spreadsheet at the beginning with the calibration coil test, but I was within 6%. So anytime you see me, plus or minus 6% on these, okay? I was happy. I would have been happy with 10%.
Unlike Paul March, you have a very stable horizontal baseline, while he had
Yes.
baselines that were drifting.
Yes. Well, it's also optimized. So all of the noise is not going to be there because it's just a very optimized system, okay?
What made the difference between the baseline that you have and the one that Paul March?
The resolution of the laser displacement sensor. So my resolution is much lower, but the arm is much longer, right? And so it sits much more still. And I can't see those little tiny jiggles, okay?
Oh, what are your timestamps?
Yeah.
Okay, this was a problem I was having with Excel, and I worked on this for hours and hours. I couldn't figure it out, but it's the UTC time, so it's right there. I couldn't figure out how to get it to say, 1 second, 2 seconds, 3, So you'll have to bear with me on that. Right. So this is actually just the UTC time. It's the universal time code.
And what is the timing of one of the calibrations?
I can't see, but I think that was like 10 seconds, something like that.
What is the noise in the residual noise?
That right there? Well, that is because my damping is slightly below 1, so it's going down and back up. So that's damping of probably about 0.8 or 0.9, a damping ratio of 0.8 or 0.9. All right, now of course, the 3D printed cavity with a Q factor of 7,000 wasn't ideal. Using the copper foil wasn't ideal. So an individual who had been following me on some of the forums sent me a cavity that he had made in China. And it was spun copper, high quality, no seams, no vertical seams like this.
Was there any coating on the inside?
No coating. Just polished bare copper.
You think that this is representative of what Professor Yang?
Yes, he's friends with Professor Yang Lan and Dr. Zhu Yu, which are two of the big M-Drive researchers in China. So he sent me this really nice cavity. Had a Q factor, it's Q unloaded factor of 32,300, mode of TE013, and the resonant frequency is 2.4114. Now, I had to include some gaskets in order to increase the size of it in order to get the resonant frequency within the ISM band. The original resonant frequency was 2.5 gigahertz, which I didn't feel comfortable leaking. There's the antenna. That was designed in FICO. I only had to make it once. That's what designing things first. I simulate 3 times, build once. That's sort of my... So I was able to confirm with an infrared camera some changes in mode. Mode TE013 has all of the RF concentrated in the small end. The first time I thought I had it, I didn't. So you can see on the first time, all of the RF is concentrated on the big end. And the second time, after doing some more simulations and better measuring the cavity, because it's actually hard to measure these cavities exactly. They're a little warped, or they're slightly off one way or the other. So with this information, I was pretty sure that I finally had mode TE013. So of course, then I have to wrap it all in insulation, because the copper is also thermally conductive, so it will begin to shed vortices in contact with air. So here's some of the preliminary results. This is a typical result. I did probably 10 runs. None of them look different, so I just picked one at random. So here we have the 2 laser displacement sensors. You can see them going along. This gray line represents power on for my amplifier and power off for the amplifier over here. This green line is the reflected, well actually I have an antenna outside, right located very close to the cavity, and so I collect the reflected power that bounces, that leaks out of the cavity. Okay, so that's like monitoring reflected power, because the power that leaks out of the cavity is the power that's reflected out. So you can see I need about 10 seconds to get myself in order and to tune it to maximum return loss. And I do that at a very low power level. And then I crank up the power. And it's about 25 or 30 watts, just depending upon, at this frequency, 2.415. I'm looking at probably about 27 watts, because it's not, the amplifier is not completely linear. So this is a very typical response.
I don't understand, which one is the optical measurement of the torsional pendulum?
These two right here. So this is a null result, everyone.
Null result.
This is a null result. And that was the result that I had more often than not. And it seems like my other results earlier were all thermal in nature. Okay, so, well, all right, well, let's try something. Let's try it even more. Let's reduce the damping ratio really, really low and run it for as long as we can until we start seeing heat. And that's what I did here. So I ran it for something like 30 seconds in here. And you can see this line here is I can monitor the temperature of the amplifier board, because it came with but I can only monitor it while it's on and off. So still a null result. Try like I may, try like I might, I could not tease any thrust out of the SIM drive. All right, so now during all of this, and this is probably one of the only advantages to testing in air, is that I can hear it.
Is that the air from the Chinese cavity that you showed us?
I'm sorry?
Was the previous slide from the Chinese cavity?
That one?
Yeah.
What about it?
Is this the one made in China?
Yes, this is the one made in China.
All of these results are from the Chinese cavity.
These results are from the Chinese cavity with the highest Q factor that I had.
Where's your power leaking?
Right below and outside.
Can you show the photo?
Well, in the photo, you have the draft enclosure right here, so it's right down here. It's right down here. It's very, very close. It's a couple of feet away. If I put it across the room, I can't detect anything, because the leaking power is so small. I mean, the amount that's leaking right here is minus 40 dBm.
Minus 40.
That's minus 40, and this is like minus 60 or minus 70. So it's a very, very tiny amount that's leaking very close. Yes, Jim?
Yeah, you have a plastic insert in the cavity.
No. No plastic insert. Though I may try a plastic insert, because that will actually allow me to get rid of the foil spacers, because you put the plastic insert and that reduces the resonant frequency. Right? So I might be able to use a plastic insert to bring the resonant frequency within the ISM band.
The 27,000 Q factor, was that the loaded or the unloaded Q factor?
The 32,300 is unloaded. This is it right here. So I've just got the VNA plugged into it. S11.
Did you measure the loaded one?
Yes, well, on this one, no, I forgot to.
Okay.
I did, but I will when I get home. I knew someone was going to ask that, but I actually forgot to do the
And how
load.
do you measure it?
Well, I hook it up here onto the machine, and I actually have another VNA on the machine that can be run during full power,
Okay.
and that's how I measure it there.
Where is your VNA?
It's part of the signal generator. It's all in one. So it's a signal generator, VNA, all in one. WinFreak, it's a really, really good.
And so after that, do you have any feed-through, RF feed-through, going to the cavity, or is it just a straight coax cable?
Right, so it's a straight, so that inside here, in the very center is where the amplifier is. It has a phase change heat sink on it, where I use petroleum jelly to phase change and absorb the heat. And then it's completely encapsulated inside of heavy insulation as well. This gives me 30, 40 seconds of quiescence in order to make my tests. Now there's one line that comes out, and it goes into the circulator here, straight down into the cavity. Any reflected power comes back out into the circulator, takes a right-hand turn, goes through the attenuators, 40 dB of attenuation, and then back into the signal generator power detector. And that's what I'm actually sitting there watching while the experiment, trying to make sure that it stays at maximum return loss.
How much power do you put in?
To probably about 27 watts.
Okay, around 30 watts.
Around 30 watts, 25 to 30, depending upon the frequency. My amplifier, starting at 2.35 gigahertz, has full 30 watts, and then it drops to 25 watts at 2.45.
What is the maximum temperature rise you see in this cavity during these pulses?
Well, see, this cavity was run probably for 2 or 3 minutes, and I got, I think, a 2 or 3 C increase in temperature.
Small.
Very, very small. Very, very small. So it's like I have to run it for 2 minutes.
How do you isolate your balance from the rest of your house?
It's in the basement, on the concrete floor. There's nothing to interfere with it. I actually live far away from any road, so there's not any vibrations from anything.
Walking?
I don't actually have that problem because remember, mine's optimized so that I don't see things I don't need to see. Okay? All right, so like I was saying, one of the few advantages of testing in air is that you can hear your machine. And one of the times when I was testing one of the older, cheaper 4-watt amplifiers, I heard a very distinct electrical hum. And so I began to think, well, maybe oscillations could be a source of error. So I built a number of devices that could, out of voice coils and voice coil actuators, that could send vibrations of different frequencies to the torsional pendulum. And these are made of, like I said, voice coils and 3D printed parts. The first result of the asymmetric shaker version 3 was promising. And of course, I'd been working on the M drive, so the only thing I had seen was noise and heat. So I was actually very excited to actually see something.
What's the ultimate noise level that you had? So you didn't see anything with the M drive, 27 watts. And what's the noise level? 0.1 micronewton?
Yes. 0.2 is what I would say is my bottom level that I can detect is 0.2 micronewtons. So I got these really cool signals that I thought were interesting. And then this here is actually a time averaged. So it is actually time averaged. It's moved. This was the setup originally before I had the liquid metal contacts. And so everything was, I had a solid state PC that I used Wi-Fi to communicate with. I had to use an Arduino. Oh wait, yeah, so there's 2 versions. This is the first version, this is the second version. Originally I was using an Arduino, which could only generate square waves. So some of the first experiments are only done with square waves. And so this is the asymmetric shaker version 4, as I was going through different frequencies, and you can see, here's 1 hertz. You can see the square wave here. Here's 25 hertz. And if you draw a moving average line, you can say, well, this is 1.9 micronewtons. You look at this one, that could be 0.728 micronewtons. 100 hertz. Here's 1.708. And the reason I don't have any of the switching transients is because I was using the square wave. Square waves don't have switching transients. Those are only in sinusoidal waves. I was able to get it all the way up to 1.2 kilohertz, 0.46 micronewtons. So I was like, well, what's causing this? So I wanted to, okay, what's causing this? So I had to have a little bit of refresher. I'm 21 years out of college. I haven't taken a physics course in a very long time. And I didn't remember a lot of this from undergraduate physics, so I wanted to refresh myself. So I set about creating simulations of all of the different types of oscillators and simulating them on a computer. So of course, the easiest one is the simple harmonic oscillator, the damped harmonic oscillator, and the forced damped harmonic oscillator. So I simulated all of those. And then these are the charts that I get from it. You should all know all of this. Here is where I use a harmonic force to drive an anharmonic, oh wait, no, I'm sorry, this is just a force-driven damped harmonic oscillator. That's the next slide. You'll notice though that I'm using a cosinusoidal drive signal there. I was getting the switching transients when I was using a sinusoidal waveform, and I thought that was bad, so I got rid of it by using a cone sinusoidal waveform. And that's one way that you can also get rid of the switching transients. Okay, so I went further, and I started studying these things called anharmonic oscillators. And they are oscillators that can spend more time on one side of equilibrium than the other and still return to equilibrium position. All right? And there are a number of ways to do that. Obviously, the first one is just put something in the way. Another way is to change the spring constant on one side versus the other. That's another way to do it. I suspect that there are probably a number of other ways, but these are the only two that I really identified. So you can see what those look like. Here I have the drive force. Again, it's cosinusoidal because I had the switching transients and I wanted to get rid of them. I didn't realize that I needed them, and you can see here we are. Here's the actual movement. It's spending more of its time on this side of equilibrium than on this side, even though it's driven by a harmonic force. All right, so now let's look at having the switching transients in place. If you have the switching transients in place, you get something that looks like this. Right? So that's a force-damped anharmonic oscillator number 3. And this is what its waveform looks like. This is where I thought, look, maybe I'm onto something. Because here I have the sinusoidal waveform. I have the switching transient at the beginning. I have the switching transient at the end, and I've got almost everything onto one side of the equilibrium position. Not quite. So I was like, okay, maybe I'm onto something here. That's whenever I decided, at first all of those simulations were done in Autodesk Maya, which my background is in computer-aided design and computer animation, and I spent a lot of time in architecture engineering, and now I'm moving into gaming, video gaming and stuff like that. So that's the perfect tool for me, and that's the tool that I'm most familiar with. A year ago, I got a 3-year learner license for Autodesk Inventor. And Autodesk Inventor is used for 3D mechanical design, simulation, visualization, and documentation. You can use springs and all kinds of stuff. It's really cool. So I set about duplicating that previous result in Autodesk Inventor using a series of spring dampers. And Jose, unlike you, I have full control over these: damping, stiffness, drive force, all of that. So I can use them to drive. So you get this 3-body problem right here, right? And as it's jiggling around, you get this waveform up here. And this waveform is anharmonic. It spends most of its time above the equilibrium position. It's got the switching transient at the beginning. It's got even the second little transient and the final switching transient at the end. Again, I thought, well, maybe I'm onto something. And now go ahead.
Just go back one slide. That first plot you have?
Yes.
What are you plotting? Is that position?
It's this thing right here. So imagine a laser shining right here on this piece. Okay? All right, so this is what this looks like, okay? This is a multi-body problem with 3 masses, spring damper, frictionless surfaces here. Imagine a frictionless surface here. Now the important thing, of course, is that right here, there's a spring damper with an elastic modulus. Now, why is that? Because there's rubber there, and rubber has an elastic modulus.
So it's a nonlinear spring constant?
Yes. All right, so here we have a nonlinear spring constant. Here we have a linear spring constant. Now, here we have rubber, here we have PZT. Technically, PZT also has a nonlinear spring constant, but it might as well be linear when compared to rubber. So, armed with that, I built this. I think you guys might recognize it. Now, I took a little bit of liberty here because I have to make it, I have to give enough spacing here so you can see it jiggle around, because I make it to where you can see it jiggle. I have a frictionless surface here, got the 3 masses right here. We've got the driver spring here, and the rubber damper here with the elastic modulus. Yes.
Sorry, but I got to make sure of what you're actually showing here. So
It's
that black
probably best to go to this one right here. So imagine, okay, this actually goes with that, okay? So you've got the laser displacement sensor shining on M3.
Where is the rubber?
On this one's right here.
Okay, that's not a...
This is the reaction mass, this is the end cap, this is the mounting bracket, and this is the rubber.
And is KZ the modulus of elasticity of the rubber?
I'm sorry?
Is KZ the spring constant of the...
K2 is the spring, yes.
K2 the spring constant of the rubber.
Right, K2 is the spring constant of the rubber. And I have it showing it as dynamic here because it's got a little
But
different.
that is not at all the mega drive.
What do you mean it's not at all? I mean, it's rubber there.
All the mega drive.
Because there are some screws.
Oh yeah, there's screws there, but the screws can be ignored.
No, the K of the screws, if you can calculate that, overwhelms by orders of magnitude.
I've got the screws in.
No, but the screws I'm talking about are not these screws here. Not this here.
Right, I've got those screws there.
I don't see them here. I don't see
They're
them.
right there. They're right here.
Okay.
And they're right here, right here. There's 3 of them here and 3 of them on this side.
So you do have a screw here.
Oh yeah, I've got screws there.
Now,
It does not follow all the way through. It does not go all the way through. It connects. That's why I have 12 here. Originally I was going to have, I think it's 4 and 4 or 6 and 6.
So
Something like that.
how do you then set the screw under tension of 3,000 psi?
We'll get to that later. That's something I have not put the entire system under compression yet. That is a future goal, is to put it under compression.
So what you're showing is no, because it's not the screws are not under tension.
Correct.
So the rubber is not under compression.
Correct.
So what you are modeling here is the
right.
rubber running against a very soft compliant, so the brass running a very soft compliant thing there, interface to the holder, which is not...
Well, my point is that at 36,000 kilohertz and the tiny amounts of movements, those screws are, and they're 4-40 screws with a fairly rough thread, they're practically non-existent. I mean, I know that it's under compression, and that is a future thing for me to do, is to put the entire thing under compression. That is something that I'm working on.
Which is irrelevant from the point of view of the mechanical analysis of the rubber.
What do you mean irrelevant? I don't think it's irrelevant because you can show that it's a 3-body problem, and if you're watching one of them, it'll show thrust.
But if you do a modeling of this from these lamp parameters, right? The lamp parameters that you have at the interface between the brass and the holder, it composed of screws made out of stainless steel, right? And rubber. The model,
Right. There's screws here too, but it's supposed to be an actuator that's moving.
I'm not done yet.
Right.
What I'm going to be discussing has to do only with the interface between the brass and the holder.
Right.
So please forget about the piezoelectric stack. Please forget about the screws that are holding the aluminum to the brass. Please forget about the aluminum cap. What I'm saying that is the incorrect model is the brass rubber bracket, which is extremely important for the effect that you're going to be showing.
Well, now, of course, it could be on either side. You could have the spring modulus on either side.
Right.
I have chosen to do it on this side. It could actually be the PZT spring modulus that's causing the problem. But I've chosen to put all of the spring modulus on this side.
Can I add something?
But the reason, I couldn't finish.
Yes, I agree with you. It's not a one-to-one comparison, but I am moving towards compression.
But let me make the argument. It only takes a couple of seconds.
Sure.
So the modulus of elasticity, these are stainless steel screws, right?
Right.
What is the modulus of elasticity of steel?
It's very low.
Of steel is
I mean, it's very high. I'm sorry, it's very high.
PSI.
Yes, yeah, it's very high.
10 to the 6.
Yes.
What is the modulus of elasticity of rubber?
Very low, like 10 to the minus 3 or something like that.
So you see how insignificant the rubber is.
Right.
Now, how,
But Jim said that putting the rubber in made a big difference, so it does have an influence.
I think that you have to take that.
He said that it didn't work hardly until the rubber was put in place.
Poetically for a number of reasons, but you also have to listen that he said that at the beginning he was using a very thick rubber pad, and then he eventually went to something.
Well, let's let Jim chime in. Jim wants to chime in. Yes, Jim?
The function of the rubber pad was initially intended to damp vibration going to the aluminum bracket, and it was quickly discovered by varying the thickness of the rubber pad that thin rubber pads work better than thick. And then it was found that by cutting away almost all of the rubber pad, it worked as well or better.
All right. So the rubber has an influence. What is that influence?
Okay, my assessment of it.
Hold on, I can't hear Jim.
The function of the rubber pads around the screws is to keep the brass from contacting the aluminum, and the aluminum damping the motion of the brass by sound being transmitted into the aluminum.
Right. But I don't think there's any argument that the rubber has an influence and it should be modeled. Okay? Now, regardless of the compression, yes, that is something, and I have a whole slide of the things I want to do. But let me just push forward with this, all right?
I have a different interpretation of the function of the rubber.
All right, that's fine. Well, we could talk about that later, because I only have 6 minutes.
And so on. It's a washer. It has no influence whatsoever from the point of view of stiffness. It has to do with the contact problem between two different materials, which in this case is the brass.
All right, well, let's see what it looks like if we actually just do the spring modulus of the rubber. And specifically, what I've found is that I think it's the relaxation modulus. So basically, the rubber is being pushed, and it can't get back into the same place in time, okay? The relaxation modulus. And now let's look and see what that looks like. Thrust is going this way, and we're looking at the displacement of mass number 3, as if a laser was shining on mass number 3. Remember, mass number 3 is what's bolted to the torsional pendulum.
You see how much the brass is...
Hold on, now, let me tell you, does anybody recognize this? This waveform? So here we have the continuous thrust signal, we have the transients, we have all of the transients, we have the full the full thrust signal right there. Here's what it looks like in detail. Here's what it looks like without an elastic modulus. Here's the actual Woodward measurement. Here's the explanation of how that presents a steady thrust. I can do a sweep from 13 hertz, from 7, now this operates at a very low hertz because I put in a very small amount of power. I did a sweep from 7 to 13 hertz. This showed me that 8.5 hertz seemed to be the best. And this, I think, is sort of the idealized form of the thrust signal. Now, the cool thing with Autodesk Inventor is I can look at the relative displacement, the energy being imparted to all of the different components. And you can see, here's the mounting bracket, here's the reaction mass, and here's the end cap. The end cap is it's fairly small and it's attached to the actuator, is the one that actually moves the most. And the important thing here is that even though the mounting bracket is showing what appears to be thrust, everything equals out in the end to 0. Okay, so let's look at the component accelerations. Here are all the different component accelerations. The end cap, the reaction mass, and the brown. Looks like the end cap is the one that moves the fastest. So it's the one that's accelerating the most. And that makes sense because it's attached to a larger mass, right? So if you have an actuator between it, it's going to push that one faster. All right, now so let's take a look at the second harmonic that's talked about and why that needs to be in phase. Now, the second harmonic, I've got the drive signal here in red, and I don't have direct access to the second harmonic because it's inside the PZT stack. But the one thing about that is that the the strain gauge that generates the second harmonic is closest to the small end cap, right? And the small end cap is the one with the greatest acceleration. And so since that one has the greatest acceleration, you would expect the greatest strain in the strain gauge at that time. And so you need both the drive signal and the end cap acceleration to line up in phase in order to get that. If they're not lined up in phase, it doesn't work. Okay?
You said the thing sunk to zero maybe a slide or two ago. Could you just hit that again?
Sure. So here's the relative displacement of all components. Here's the center line. Here's how everything in the entire system moves. And how it all equals out at the very end to zero.
Okay.
Even though this one piece, even though this one showed thrust, because you're not looking at all parts of the system, you're not seeing the whole system.
That's the mounting bracket is the connection with the rest of
Right, but everything else is moving too. And that all needs to be considered. Yes, Jim?
Yeah, what you're not taking into consideration is that in this model, without a mechanism to get that thrust of the sort that we're talking about, is that you're generating a displacement of the material. The mounting bracket is being displaced because of asymmetric oscillations in the stack.
Yes.
When that acts on the torsion balance, however, producing a displacement in the mounting bracket by whatever mechanism you're using inside that's allegedly conserving momentum, all you do is produce a transient on the thrust balance. So you get a transient, and then
I think I've got some slides that will address that. I've got some slides that will address that.
remember to zero itself because you're producing a displacement, not a force.
Okay, I'll address that in a slide. I have a slide on that. Let me just, go ahead.
Just wanted to point out, the Empire State Building, if you put a strain gauge at the bottom of it, that's the part that is supported. That's kind of the burial theorem, you know.
Right.
What weight does the foundation bear it? The internal stresses in the rest of the building don't matter. I guess I'm just, you're showing a force on the bracket. And then you're showing forces on all these other things, but the force on the bracket is the connection to the rest of reality.
I actually deleted the chart that actually had the forces. These only have accelerations and displacement because I thought it was too confusing. So I actually deleted. I thought I had 3 in a row.
We're assuming that Newtonian, something like Newtonian physics. I guess I'm puzzled as to why you're including the other things.
I need to move on because I only have 30 seconds.
The connection with, just like the base of the Empire State Building.
Let me get to that. Okay, the effect is reversible by rotating the device 180 degrees, which I did in simulation. Okay, so let's get a little bit more complicated, right?
So if you add it, you get zero.
I'm sorry?
If you added the reverse one, if you added both, you have zero.
Yes. Yes. Okay, so let's get a little bit more complicated. Let's try and build the entire device here. And can I get just a few more minutes? All right, I'm almost done. I only have a couple more slides. All right, so I basically did the same exact thing, except I tried to include the simulation of the bracket that attaches directly to the torsional pendulum. Now, the entire torsional pendulum is only, as far as I could tell, a 5 degree of freedom system. So I'm only missing 1 degree of freedom so far. That's part of the future stuff that I want to do. Create the entire torsional pendulum and everything in simulations. Excuse me. So what does that do when you run the simulation? You find out that this is all transferred up the stack. So, and then this is the displacement that we were originally measuring has become distorted. And the original thrust signal is then transferred up the stack, which I thought was really cool. And the more damping, the more vibrational dampening, the better it works. If you have like very low damping, it messes the whole thing up and it doesn't even work. All right, armed with that.
When you reverse it.
It does the thrust reversed as well. I didn't, but I mean, I know that's going
When
to do.
you add them, you get 0.
Yes.
But you're aware that Jim reverses it, and what he's showing you is the...
Well, hold on, let me I've not added them together to see if they come to 0. I just assumed that they would. I've not actually added. I should probably do that. Okay, armed with that information, none of the devices I had was a 3 degree of problem. But then this was just Friday, I had the idea, well, what if I combine 2 of them together? And then I've got a 3 degree of freedom system. And what happens if I run that? So here's my 3 degree of freedom preliminary real world tests. 3 micronewtons, 3.52 micronewtons, 10 hertz, 15 hertz. Let's reverse it. Effect is reversible. 1.3. I had adjusted the amplitude, that's why it's less. I had turned it down between tests and didn't turn it back up to max. Exploring higher frequencies in the simulations. I've got it working up to 200 hertz. At 1 kilohertz, I found this really weird one that reverses in the opposite direction. It looks completely different. In order to solve for 36 kilohertz over 5 seconds, it's non-trivial. You have to increase the solver accuracy. You have to increase the time step to at least a minimum of 100 time steps per hertz. And on a 36,000 hertz signal over 5 seconds, you're talking millions of time steps in order to simulate this.
They're called stiff equations, and they're very difficult to solve because they have very small increments.
Yes. So, obviously I want to increase the driver force, because to do all that, you got to increase the spring. I want to do chirp signals, finite element analysis. I don't know why. Oh yeah, bonus. I want to simulate the components under compression as well. I have 3 predictions. Testable prediction number 1. Long stroke PZT actuators generate the stroke by expanding this way rather than this way. Right? Such actuators should be able to generate the effect without accelerating the PZT stack in relation to the end masses. Only problem is they're expensive. Testable prediction number 2. METs mounted at a greater distance from the torque bearing will displace the torsional pendulum less. Therefore, they will appear to produce less thrust. And the way that works is a pretty simple, you can see how that works. Same actuator mounted at a different radius would obviously displace it, would appear as more thrust. And this seems to be the case already with the repetitions being lower. Then, all right, testable prediction number 3, and this sort of sums everything up. If the phenomenon can be simulated using only local mechanics, conservation laws apply. As such, MET should only oscillate when free in space and not accelerate. And there are ways of testing this, of course. MIT's maglev CubeSat testbed, this other one here. I'd like to simulate these first because you might be able to use some kind of parametric oscillation to make this move around. I'm not entirely sure. That's just a thought I want to throw out there. And that's my presentation.